Hi, in this module I'm going to present the particle filtering algorithm for performing approximate inference in hidden Markov models, which is really useful when the size of the domain of the variables is very large. So let's start with our familiar object tracking HMM. In this case, for every time step, we have a position HI of an object, which we don't see, and instead we see some noisy sensor readings. So the probabilistic story of object tracking is as follows. Each one, the first object position, is generated uniformly across all of the values, 0, 1, 2. Subsequently, H2 is generated addition on H1 via this transition distribution, which goes up with probably 1/4, stays the same with probably 1/2, down with probably 1/4. Then we transition to H3. Now, at each time step, we get a sensor reading, E1, E2, E3, conditioned on the respective locations, and that's governed by the emission distribution, which takes HI and goes up by 1/4, stays the same with half, goes down with probably 1. So now you multiply all of these local conditional distributions together, and you get one glorious joint distribution over all the object locations as well as the sensor readings. That's our HMM. So now, given this HMM, we can ask all sorts of questions on it. In particular, we looked at filtering and smoothing questions. But particle filtering, as the name might suggest, does filtering. So let's focus on filtering. So in filtering, we're asking for the position of an object at a particular time step conditioned on the past. So time step 1, we're asking for, I'm looking at only the evidence at time step 1, and it's like, where is this object? At time step 2, I now have 2 observations. Now I ask, where is the time object at time step 2? At time step 3, I have 3 observations, and now I'm asking for where's the object at time step 3. So now I could apply forward-backward algorithm to this scenario, and that would work. But the problem is that if you have a setting where there's many location values for HI, so in our simple example, there's only 3, but in practice, there could be 100,000. And in that case, forward backward is going to be really slow because its running time scales quadratically with the number of domains. You have 100,000 squared, which is not a nice. So the goal of particle filtering is to realize that, well, you have 100,000 possible values, but only a very small fraction of them are really likely given the data you have. So to start introducing particle filtering, let us revisit beam search, because structurally particle filtering and beam search are analogous. So in beam search, remember the idea was to keep track of at most k partial assignments, which we're going to call particles now in the particle filtering lingo. So beam search starts with a candidate set of only one assignment, which is the empty assignment. And it's going to go through each variable in turn from 1 to n. And now we're going to, for each of these partial assignments, for h1 to hi minus 1, I'm going to take that, and then I'm going to consider all possible values I can assign to hi. I'm going to extend that assignment. So now we get a bunch of assignments from h1 to hi minus I. And now I'm going to compute the weight of each of these candidate particles, and I'm just going to take the k highest weight particles. So let's recall beam search on this example here. Here we have our object tracking HMM. We have the variables and all the local conditional distributions, and I'm observing 0 to 2. So beam search starts out extending to variable h1, and it produces 0, 1, and 2 are the possible particles with weights, these probabilities here. And I prune, which does nothing because k is 3. And then next, I'm going to extend to H2. So each of these particles kind of multiplies into 3 particles. And now the weight of each of these particles is going to now include the factors, which are the transition into H2 and the emission of E2 equals 2 given H2. Now I'm going to prune down to 3. I'm going to now extend to H3, and I'm going to prune. And at the end, I get a set of particles. So here I have 0, 1, 2. I have 1, so 0, 1, 1. I also have 1, 2, 2. And each particle has some weight. Normally in beam search, we're interested in the presented in the context of finding max weight assignments. So in this case, you would just return 1, 2, 2. But in the case of particle filtering, we're interested in answering filtering queries. So what we're going to do instead is we're going to normalize the weights over all the particles to get an approximate distribution over assignments. And now we're going to pretend this is a joint distribution over H1 through Hn given the evidence. And now I'm going to just sum probabilities to get any approximate smoothing query, filtering query, I like. So this is fine, but it has 2 problems with it. One is that the extend step is slow because it requires considering every possible value of HI. So sometimes you can be clever. You don't have to enumerate all the values in the domain. And you can only enumerate over values that are going to have positive weight, but even that could be a lot. So the second problem is that we are greedily taking the K particles with the highest weight. So this is going to, as we'll see later, doesn't provide enough diversity. So we're going to have to do something about it. So particle filtering is going to solve both of these issues. And particle filtering is going to contain 3 steps to replace the extend, prune, 2-step procedure of beam search. So propose, wait, and resample are the 3 steps, and we're going to go through them in turn. The first step is propose. So in general, you should think about the set of particles as an approximating a certain distribution. So in general, the filtering distribution is the probability of the variables that you are considering conditioned on the evidence so far. And suppose we have just 2 particles here, 0, 1, and 1, 2. So now the proposed step is going to take each of these particles, and I'm just going to sample a value for H3, the next variable, given the transition distribution. Remember, it was up and down with probability 1/4, and the same with probability half. So that is going to produce these extended particles conditioned on the same evidence. So for example, I'm going to take 0, 1. I'm going to, now that will produce this particle with probability half, because I'm just keeping the value the same here. And I'm going to take this particle and I'm going to extend it to 2, and that's also going to happen with probability half. Now, this is a random algorithm, so I could have sampled from the distribution. I could have gotten 1 here. I could have gotten 3 here. But let's just go with 1, 2. So in the next step, I'm going to wait. So you should think about these particles as a guess as to what H3 is going to be. But we need to fact check this guess with evidence. And so the weighting part step is going to assign a weight to each particle, and that weight is going to be the probability of the new evidence I got conditioned on H3 here. So this is going to produce a set of new particles which are weighted, representing the distribution, the H1, H2, H3 condition, all the evidence so far. So let's work out this example. So for the first particle, I have H3 equals 1. So H3 equals 1. It's going to generate the evidence E3 equals 2 with probability 1/4. So I have a weight of 1/4 attached to the first particle. The second particle has, this should be a 2 here actually. So the second particle has H3 equals 2. And I'm going to look up this table, and that's going to have weight 1/2 because the probability of generating a 2 given a 2 is 1/2. So I have a weight of 1/2 on this particle. So now at this point, I have a set of particles that represent the advanced filtering distribution. But notice that the weights are not the same, and some weights are small, some weights are big. And in particular, the particles with small weight are kind of wasting space. You should think about the K particles as kind of a limited resource for representing this distribution. So if you have a particle with weight 0.0001, or maybe even 0, then certainly we shouldn't be wasting one of the valuable K slots for that value. So what we're going to do is to reallocate our resources via resampling. So in the resampling step, we're going to normalize these weights and draw K samples. So normalizing these weights produces this distribution 1/3, 2/3. And now I'm going to draw K samples from that distribution to redistribute. So the resulting particles are still going to represent the same distribution, but slightly in a different way, without weight. So I'm going to sample. Maybe I get 1, 2, 2. I got that with probability 2/3. Sample again, and maybe I get the same particle again, 2/3. Now, of course, this is again a random algorithm, so I could have gone the first one and the second one, or the second one and the first one, or the first one and the first one. So now you might wonder, why are we resampling? Why leave the result of the algorithm up to chance? So to see why, consider the following setting. So we have a distribution over a bunch of possible locations. And suppose that distribution is very close to uniform. So you can see, maybe you can see that there's a slightly higher probability in the middle, but it's pretty flat. So now if you did beam search, which takes the K possible positions with the highest weight, you would end up with this. And so you would end up with all the particles clustering around the middle, which is really not representative of the distribution, because you have all these positioned out here with non-negligible probability mass, which have no support. So it's kind of like putting all your eggs in the same basket, or the same K baskets, I guess, as well. So instead, if you resample or sample from this distribution K times, you're going to get something more like this, which I would argue is more representative of the distribution. So in cases where most of the weight is on a few locations, sampling versus taking the top K is not really a big deal. But when there's high uncertainty, as in this example, sampling is really important because it allows you to maintain the uncertainty. So now we're ready to present our final particle filtering algorithm, which is, again, structured very similarly to beam search. So like beam search, we initialize with the empty assignment. For each of these time steps, we're going to propose, weight, and resample. So here we're going to propose. We're going to take each assignment to H1 through HI-1, and we're going to look at the transition distribution and generate one possible assignment to HI, and I'm just going to take that. So in beam search, I'm going to consider all of them, which can result in a blowup, but in particle filtering, I'm going to only look at one. Now I'm going to weight the particles based on the evidence, which is this emission distribution. And finally, I'm going to redistribute my resources by normalizing this weight distribution and drawing K particles independently from that distribution. Okay, so let's see a demo here. So here I have my object tracking HMM. I'm going to run particle filtering with 100 particles instead of beam search. So I'm going to start out with extending to the just the first variable, and now I have I have 100 particles, but 38 of them are 0, 33 of them are 1, and 29 of them are 2. And these are the weights. I resample, and now I redistribute probability to 0 and 1 with these particle counts. So now I'm going to extend, and notice that before I had 73 particles at 0. Now 51 of them go to H2 equals 0, and 22 of them go to H2 equals 1. And then I'm going to resample, which redistributes the particles again. Now I'm going to propose and reweight. Now all the particles are all over the place. And now I redistribute mass so that the particles are used more effectively. Okay, so now at the end, I have now 100 particles covering all of these different assignments. I can simply count the fraction of them for that satisfy various values of H3, and I get my approximate filtering distribution over H3 condition on evidence. Okay, so there are two ways to make particle filtering more efficient. So particle filtering, we've cast it in terms of generating a distribution over complete assignments to all the variables. But if you're only interested in filtering queries, which look at the last variables, then what we can do is, instead of storing all the assignments, we only need to keep the value of the last HI. So I'm going to only look at H3, because this is sufficient to continue the algorithm forward. And furthermore, if you have multiple particles that have the same value, you can actually just store the counts, as we saw in the demo. So 1 occurs twice and 2 occurs 3 times. So now let's visualize particle filtering in a more realistic, interactive object tracking setting. Okay, so here we have a grid, and we have an object that's going to be moving in this grid where we're trying to determine its location. So the HMM is going to have a transition distribution that places a uniform distribution over moving north, south, east, west, or staying put. And the emission distribution is going to put a uniform distribution over locations that are within 3 steps, either vertically or horizontally. So you can kind of see this definition of this emission distribution, which only depends on the x distance and the y distance, and it's going to look at a uniform distribution over basically a box. Okay, so if I hit Control Enter here, we can see the observations. They're very noisy, and we're trying to guess where the object is. So I don't know where, somewhere. So what we're going to do is we're going to run particle filtering. Let's say we have 10,000 particles. We hit Control Enter again. And now what we're going to see is a red blob. And this represents where the particles are, with the intensity of the particle representing the number of particles at that particular location. So you'll see that this is our kind of best guess of where the object is. Okay, so you can see how well we're doing by showing the true position. So let's see where this object actually is, and we'll see that we're tracking it, rather well. Sometimes I think you'll notice that it might mess up, but on the whole, it's pretty good. So also notice that the red blob, where it thinks the object is not fooled by where the observation is, because there's enough noise here that what I'm modeling the particle filter is doing is that it's essentially kind of smoothing out the noise. The noise is jumping around a lot, but it's kind of tracking and knows that the object can't be teleporting and it's moving only by one step at most each time step. So you can play with this demo a bit more. We also have implemented, instead of this box noise, you have Gaussian noise, which looks kind of similar, more of a spherical blob. You can also play with it. There's kind of really weird looking noise, which places uniform distributions over all positions on this lattice that have a certain kind of parity. Okay, so in summary, we've presented the particle filtering algorithm, which allows us to answer filtering questions of the following. Where is this object at a particular time step given the evidence so far? And the key idea is using particles to represent this approximate distribution. So remember, particle filtering has 3 steps, which is used to advance the set of particles. First, we propose where we take particle and transition them to the next time step. This is a guess of where the object is going to be at the next time step. Then we're going to fact check our guess by reweighting the particles based on the emission distribution of what we actually saw. And then we're going to reallocate our resources by resampling, and this will allow the particles to occupy the regions with higher weight. So unlike forward-backward algorithm, this particle filtering allows us to scale up to cases where there are a large number of locations. And also, unlike a beam search, it allows us to maintain better particle diversity, especially in situations where the distribution is close to uniform. So now particle filtering is also called a sequential Monte Carlo, and there's many, many more sophisticated extensions that I haven't covered. In particular, particle filtering works for general factor graphs, not just hidden Markov models. And I encourage you to read up and learn more about it. That's all.